Welcome and good morning to the 8th lecture of Type Systems for Correctness and Security. As it goes with the semester, the audience is shrinking, but that shouldn't hold us back from having fun today. with object orientation. So today I'm going to introduce you to the concepts of object orientation when it comes to typing. So this is going to be pretty interesting. We're learning two different systems for that, but before that we're going to get started with a little bit of repetition, meaning the exercise number 6. Again, if you have comments or questions, exercise here. Let me scroll that up a bit. Yeah, that should be it. So it says the multi-step evaluation relation is the reflexive transitive closure of one-step evaluation. That is, it is the smallest relation, such as one. This, if we have, if we can evaluate t to t prime and t, then t also in multi-step evaluates to t prime, and if t multi-step evaluates to t prime to t for all t, and if t is in multi-step evaluation evaluating to t prime and t prime's multi-step evaluating to t prime prime, then it is directly also so. So basically like the reflexive transitive closure of that thing. And now the idea was to rephrase that as inference rules. Well, that shouldn't be too hard for you at that point. Let me guide you through this a bit. I do have enough light here. Okay, great. Good. So the first task was to reformulate what was given there. And the nice thing is, it is already given as a premise and a conclusion. So if then, so what you basically do here to get that started is you take the thing before the if and put it into the premise. So t evaluates to t prime, and this concludes, this is the then part now, that t multi-step evaluates to t prime. Oh, that was the easy part. So now second thing goes, this is just this is just an axiom. So this is the reflexive part. So the multi evaluation is reflexive such that t is always in the relation of t, and it does not have a premise because we do not have any condition under this holds, because it holds for all t. And then the third part that we had here has again an if, but with two premises. So you need to take both of them into account and put that here. Is that? That's both multi-step. T prime prime. And then the conclusion of this is t multi-step evaluates to t prime prime. No, there you go. And then you have created inference rules for all of them. So that was the first exercise. It's just a thing about the mechanics of this, and so that we learn, okay, how to formulate such relations in a way that they can be seen as inference rules. No? Good. So we have, does this all fit? No. So just to quickly walk you through, second part of the exercise. You all should have done this before, so I'm not telling you anything new. So we assume we have the simply clubbed lambda calculus and some rules for if terms and Boolean types, so we can work a little bit with that. And there is an assumption given here. We'll just quickly scroll that into view in a second. And the idea is, can you show that the following type assumption holds? And if this is the case, we create a full derivation tree, and if it's not, there is there a type that this expression has? If this is a different type than the given one. So this is a rather lengthy thing. So I'm going to help myself with introducing a few shortcuts, but I'll do this along the way. And the way that we do that is we take that part and we want to show that it holds, so it goes to the bottom of the derivation tree, way down here. And we need to simplify this a bit because this is a bit lengthy. So let's get started a little bit. So we have the gamma turnstile symbol again. And what we cannot simplify is, of course, lambda x dot lambda y. This is given. And then we start with if x then y, and then we have the one else branch, but again leads to another thing. So let's simplify this a bit. So else, now we need a function for that. I'm just to stick with the solution, calling that gamma. And let's note that down here what gamma is. And gamma is lambda b, lambda c, lambda d, and the body is if b, then alpha, else beta. And now we need to define what alpha and beta is, because these are kind of the parts that we need to know. And what alpha is, it is this part in the first part and then part here. So it's parentheses a dot a, so the identity function applied to true. Remember, we don't evaluate here, we only just syntactically replace, because I don't want to fill the whole page with the whole term. So you can always do this, because it's don't want to mess up everything on your paper. So, and then we need to define beta, and beta is of course the other part, and I'm just taking this down from the exercise. So lambda e if c then e else d, and we apply this to true, as we can see here in the term that we have there. So we just exchanged this first parenthesis here, so the else thing. So what we do is we write gamma and then x, y, and false. These are the arguments given in the right hand side here on the exercise sheet. So, and all of this should be bool to bool to bool according to the statement. So what's our first thing? So what we have here is, so the first outmost term here is an abstraction. So we try to type that abstraction. So we usetabs. So now we go into typing. And in doing this, we push the first part here, the first type, in the assumptions. So we do gamma x bool, and under these assumptions we have lambda y if x then y else gamma x y false. No. And oops, no. And now we've taken the first function type and put it on the left side. So we write here bool. Bool. Oh. I hope you can read this down there, but I'm also saying this. Good. And then, of course, the outermost term here is again an abstraction. So we apply the t-abs rule again. And then our typing environment grows a bit bigger. Bool. Bool. And then we take the inner term, which is if x, then y, else gamma. My gammas get sloppier as I write. X, y, false. No. And of course, as we've pushed the left part of the function type again up here, it's just bool. Okay. So the outermost statement here is an if. So we apply the t-if rule. We can take the one from the B language. Basically, it's the same syntactic thing. And this is the extension, like mentioned at the beginning of the exercise. Good. And the t-if rule has 3 premises. So the first premise says we take, let me just quickly, for convenience, define a gamma prime as gamma bool y bool. That's not done in the solution sheet, but I don't want to repeat myself over and over again. And this is basically this here. So this is gamma prime now. And so the first premise is about the condition up here. So it's gamma prime x bool. And as we know that our return type should be bool, then we would also type the 2 arguments here, the two sub expressions here as bool. So under the same assumption of gamma prime, y would be bool. And under the same assumptions, of course, it would be that nice gamma. Gamma xy false would also be bool. So, first thing that we need to check is x of bool. X is in the set. So the premise holds. X bool, this relation is in gamma prime. Now we need to check if y is bool. Y is also assumed as bool. So y bool is also in gamma prime. And then we need to take care about the rest here. And as you can see, this is again the t-abs rule and the if rule and so on and so on and so on. We can now do this and see that this also results into bool. Because it is bool if the argument here is b is a boolean. We can type it as a boolean. That works fine. And because x is bool again, so x is b is substituted by x, which is bool. This is fine. Y is substituted by c is substituted by y, and c is here. A again. What's A? A is this one. Also, it's just alpha. It's just the identity of true. So this thing is also boolean. This works. So it's beta boolean if C is bool. That's fine. E and D, which is Y and false. Which is that? Oh, that's the D. This is this one, and E. I don't know. So you can basically type that. the whole thing as bool bool bool. So this works. No? I would just repeat at this point. Okay. At this point, we're just talking about different things. Good. So 6.3 was more of a knowledge question, and it asked, what is the difference between the record and the variant extension? Remember, this is kind of a record. Yeah. And the type of the thing is x type this bool, sorry, as a natural number, y type this natural number. That was the last exercise that confused me. Yeah. So this is a record, and the variant was more like something like this. So it was so you had this we had the thing with the weekdays, and we had things like and so on and so on. Now we can go on forever. So the idea between a record is just a collection of multiple terms in a single term. Yeah? And variants were a different thing. Variants were choices of multiple types that can be treated uniformly. So you can have a variant type and have a function that takes that variant type, and you have multiple types that you can treat uniformly. No? That was the idea. We had this idea with the selection of the weekdays and then giving the next weekday after and so on, or the optional types that we used. These were all applications of variant. So let's look at exceptions. So this was a multi-part question here. So here we said in this task we will inspect the type of the error term more closely, and we will examine the exception type T exception as various definitions. And so the first part here, the 641, asked, okay, recall that error can assume any type. Wouldn't it be simpler on the formal side just to require the programmer to annotate errors with its intended type with ascription in the context where it is used? Good. So how would this look? So you would have something like a function, and you can say that, okay, you have something like error as bool, something like that. You could do that. Well, this is ascription at that point. This is what's given here. The problem is that you would break type preservation. Let's take something like this. So let's take a term like this, and I constructed something for the solution that looked like this. So you had a function, identity function for natural numbers, and you apply this to this function, which is a constant, takes a bool and returns a constant. And then you would have something either directly or through evaluation error as bool. So syntactically, this is a correct term. Also, it would evaluate to something, probably error. So this should be kind of fine, but is it helping typing? So let's have a look. So error as T is the type annotated syntax for exceptions. This is what we have here. And if we would evaluate this, we would have something like this. So this would evaluate, of course, because you can apply, this is a Boolean, this is fine, and you can apply this function to this term here on the right side. So what you would not get is 5, of course, because the evaluation for things would give you something like this. So the left part would stand. We're not evaluating the function. This is already a value. This is fine, but the right side isn't. And you would get this. Yeah. And the problem with that is that the return type of this function is natural number, but now, as your evaluation rules go, you would now have an error as bool. You now would have a Boolean. So you cannot apply this argument to this function. You would get stuck. So you also heard progress, interestingly, but first you heard preservation, because the type of this term should be so the type of this function is a bool to nut, as you see here. However, as you see in the result here, you would not get a natural number, you would get a Boolean again, and this hurts preservation. That's the nature about errors, because errors propagate from the point where you throw them up until the top level of the program, and this is why we have to view it as many types. And with the t-error idea, we can actually do this with the typing of errors. And we now explore that in the second part. So this would not work. So let's look at the second part of the exercise. So the second part says, is that here? Oh, I have to scroll that up. This would be interesting. I have to really tighten this a bit. Okay. So give examples using the 3 different suggestions for t-exception. Quickly type check them by using derivation trees. So let's just do that. Let's do that for natural numbers first. And the idea here is that the type of exception is now a natural number. And you can use this. You can use this in a term like this. So lambda x nut. Let's do this. Just an example. If equals x0, then true, else raise 1. And as you can see, we're giving here a Boolean, and we're raising an error that is internally a natural number. And now the idea is, what is that to be typed? So the general thing goes, the function goes from natural number to Boolean. This is the thing that we want to show. So let's do a derivation tree for that. You can see the bottom of my page. Up until this point, probably. Or I can push this a little bit. Okay, good. So the idea is, can we type this term? If eq0, x eq0, sorry, then true, else raise 1. So we cannot truly decide because it takes an input value, as you can see here, and this should go from natural number to bool. No, there we go. And of course you see, rightfully see, okay, this is an abstraction up here. So you start with t-abs and you extend gamma by x is natural number. So this is the assumption here from the input parameter. And then your idea is, because you take the right part of the function type and put it here on the right part again, So if EQ x0, then true, else raise 1. It should be of bool. And of course it's an if. You apply t if. And if EQ x1, so the EQ x1 should be bool. We don't have EQ right now here, so we assume this is good. Don't write it. True should be Boolean. This is fine, because t true gives us that. And then the raise 1 should be Boolean, and this is given by the TEXN rule from the lecture. If we can type 1 as TX and EXN, sorry, the exception type, and the exception type is natural number. This is fine, so the whole thing checks out fine. And this here is the critical part. We couldn't do this before in this part because we didn't have such a rule. We cannot decide that this term, this ascribed term here, is actually an exception type, but here we can. Here we definitely define an exception type and have checked out that the term that we had inside of the race is also matching this exception type. So this was all good. Good. On the solution sheet, you would also find the proof here for the EQ x0, but this does not help us very much at this point. I'm just leaving it out. So just you have the completeness in the thing. Also in there you have exceptions for strings with a little bit more complex examples over a let and like in the record type and so on. Then we also have an example for variance where we use different error types basically. So there was an example using an illegal argument and an overflow. Oh, let's just do this. Just for the sake of the argument here, and also to repeat variance again. So let's do this with variance. So the exception is this variant type, meaning that we had something like illegal argument, which is typed as unit. We don't need any more additional data, and overflow also as a unit because we don't need additional data. And then we have a term like this, lambda x nut, if greater or equal x999, then raise overflow equals unit. So this is the type and this is the term of a variant, just to be sure that you got that. And the else part would be the successor of x, because we cannot count over 999. This is okay. And all of this is a natural number again. And if we would type that, sorry, no, it's not a natural number. It's a function going from natural number to natural number. And let's just quickly do that. Let's call that a. And we say that a is of type natural number to natural number. Yeah. And of course, we start with the abstraction rule and say the return style, and then the inner part, and let's call the inner part of this the inner part of that let's call B, just so we don't write ourselves to our death. And this is B, and this should be a natural number, because the successor of x is a natural number, and the error should be typed as that thing. And B is in the form of an if, so we apply the t-if rule, and that means that greater equal x999, oops, no colon, x999 should be a Boolean. Let's omit this here and assume this is true. And this is the critical part, raise overflow unit should be of type nut, yeah, because B is nut. And this is given again by the T exception rule if overflow unit can be typed as T exception, which is the case, because it is in this term type up here, and then we're all good. Good, and the successor of x is naturally a natural number by the rule of the T-app rule and so on. You can just see that, or you have a definition for successor somewhere as a syntactic construct, also works. Okay, so exception types, pretty amazing. Good. Yes, it scrolls into view. So references 6.5. So the idea here was, the question was, can you find a context gamma in a store sigma, small sigma, and two different store typings, big sigma 1 and big sigma 2, such that both two store typings find that store. Good. So the idea, the question here is basically, is store typing unique? Okay, for this, let's construct such a state with a single location. So small sigma. And then we have a location L. And this maps to lambda x, going from unit. And for this, we dereference L and apply x to this. Yeah, let's assume we can do this. Yeah. This is a dereferencing of the same location. This is fine, and as you can see, it's a function going from unit to probably unit. This is all pretty neat. You can just apply x to that, and it will result in an infinite loop, basically. And you basically do not need anything in gamma. You do not need to type anything because you don't have any interesting variables here. You might have that x, but who cares? And the idea here is why then can we find two store typings, so the typings of these locations. That works pretty well. And as this definition goes, you can pretty much generate a few store typings. And the first one would be something like this. L goes from unit to unit. So This naturally holds. You can see that. Well, it seems to be unit. Okay, this is good. But in a second iteration, because you have the dereferencing here, you could also do something like this. So a function going to a function from unit to unit. This is also a proper store typing for that store. I bet there are a few more solutions than this out here, but the trick usually is here to find something that dereferences itself, and then you would have something. You could, of course, have more complex things that dereference other things and so on. This would also probably work. Good. Are there any questions anymore for exercise number 6? Good. If it's not the case, if it's the case for something else afterwards, just let me know in the comments in Panda, and then we'll know. Okay, then let's do a 10-minute break, roughly 10:48, 10:50-ish, something like that, and then we continue with the lecture, and then we'll walk through object orientation and get that included into lambda calculus in a different system that I will introduce you today. Can I repeat 6.5 again? What part? I mean, you can basically scroll back in the live stream and hear myself speaking again. I don't know why I should do this again in the live stream. Can you frame that question a little bit more closer? What the question actually was? Thank you, great. Okay, then let's do a 10-minute break. Let's say 10:50, and then continue with the lecture.
Comme s'il était faux, même toutes les rats sortaient sans trou. Venez tous, chaque soirée joue dans la rougette des pièce dans son chapeau. Dab dab, bidi 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 ba, les rois du jasmineux, marbini de bas, sentimental, venez tous, ces soirées jouent dans la rue, les rois du geste. Manouche. techo, por el agua y por el fuego, por tu espalda cuando duermes, la tarántula te puede picar. Cuidado, desde el suelo vigila la tarántula. Ve con cuidado, desde el techo vigila la tarántula. La tarántula vigila. Desde el suelo, desde el techo. La tarántula vigila. Desde el mar y desde el cielo. La tarántula vigila. Desde dentro de tu mente, la tarántula te puede picar. Ponte la inyección. Si te pica la tarántula, no hay otra solución. Si te pica la tarántula, aprende la lección. La tarántula te puede picar.
Question on variance and natural number types in the chat, which I hopefully answered. Oh, interesting. And the thing just ate my... oh, the thing just ate my angel brackets. Interesting. So does this work? Oh, this works. Okay. So a variant type. You have to remove the backslashes from your reading. And my chat message doesn't make any. Not the same as. I hope this time it won't eat my notation. Okay, Panda chat sucks. I'll post this in the in the Panda forum later on. Yeah. Interesting. Yeah, that's supposed to be securing not being able to enter HTML entities or scripts or so, I believe, but yeah, well. Good. I add that to the Panda forum. Yeah. Panda chat. Good. Onwards to our topic for the lecture. So today's lecture is about object orientation, And as such, we have to define first what we mean with object orientation to be a little bit more formal. So what is actually object orientation? What is the thing that you supposedly do when you do object-oriented programming? So what is that concept? And the first thing that you have is you do have multiple representations of basically the same thing. It will get a little bit clearer what I mean with this later on, but keep in mind you have multiple representation of maybe the same thing. You do have encapsulation. This is something that comes very natural when you do things like Java programming, where you have like privacy modifiers like private, public, protected, and so on. You do have things like getter or setter methods. So not everything, not the entire state of an object is exposed to the public. You can really choose how to do this and have like internal and external state. Of course, you have subtyping. And subtyping is very important in object orientation, because then this actually facilitates the multiple representation part to some extent, and also it helps you to have program against interfaces and not against actual implementations. And by this, you also have inheritance. Now, what's the difference between inheritance and subtyping? Okay, in subtyping, this is just for typing. An inheritance means that we're going to inherit the members of our ancestor classes, and that we're going to have all the same state and methods that we had before, functions that we had before. And open recursion. Open recursion is that you can use the same methods on the same object from each other. So in Java, this would be the this modifier. In other languages, you have the self modifier, where you actually have a reference to yourself. We're going to actually do this with the lambda calculus, which is not going to be easy, but we're making it happen. And once you get that into your head, this really makes work. This, of course, is the reason why we bothered with recursion in the first place. Multiple representations. Let's walk you through this a little bit. So when an operation is invoked on an object, the object itself determines what code gets executed. So two objects responding to the same set of operations may use entirely different representations carrying an implementation. So you have two objects that both respond to this method M. Of course, totally different implementations may happen. And we call these implementations the object's methods. So this whole thing is an object. There is the so-called method body inside of the object. It's not the entire object. It may have more methods and method bodies. And then you have a method invocation. So you invoke a method on an object. This is terminology that should be fairly familiar to you when you programmed in Java or different program languages like it, and then would have that. And this is what we call dynamic dispatch. When we call a method on an object, the object itself decides what gets executed. And the other thing is, even though you do a method invocation on a reference, you do only dynamically decide which method body actually gets executed. This is very important because when you have subclasses, then you don't, and you have a variable that has the superclass as its type. Then you don't want the supertype implementation to be executed. You want the subtypes implementation to be executed, much like in Java. And the feature that enables this is so-called dynamic dispatch, and we're going to implement that. Good. Encapsulation should be fairly natural. So the general rule is that the internal representation of an object is generally hidden from view outside of the object's definition. So from an from an object's definition from the outside, we do not learn anything about the internal representation, and we should not rely on that. What also this means is that only a small and easily identifiable region of the program is affected from changes of this internal state, because no external dependencies are there to be considered. So this dark blue ring here is the external representation, and the blue circle in the middle you can imagine as kind of the internal representation of an object. Should be fairly larger. That might differ on your specific implementations. Subtyping. So the type of an object is its interface. We already know that from Java. And the interface is just a set of names and types of its operation. That means methods. And the object's internal representation does not appear in the type. That is true for almost all object-oriented systems out there. The object's internal representation does not appear in the type. So in typing something, you would do not know its internal representation. This is fairly critical because this allows all of the neat things that you have in object orientation, meaning polymorphy or things like that. If you would not have that rule, your client code may depend on the object's internal representation to some degree, or it may see that. So subtyping in object orientation we informally define as follows. So if an object's interface J defines fewer operations than the object's interface I, then J is a supertype of I. This is a little bit more dynamic than we know in Java. In Java, we do actually have to factor out interfaces and superclasses ourselves. Here, it just comes naturally and automatically whenever we define a supertype. Whenever we define such a type. Good. This is also pretty similar to the subtyping of records, to be fair, because fewer operations means fewer fields in the record. And this is very similar to the subtyping of records. Let's move on to inheritance. So objects that share parts of their interface might also share some behavior. Hopefully. And the idea is to just implement this once, rather than to copy every function code to every subtype. And this is inheritance, so the automatic behavior that you can reuse behavior. And the concept to reuse behavior via structures is called a class. And there you have the difference. I'm always getting that question, what's the difference between a type and a class? So the type is basically the interface, and once you reuse behavior via structures, then you have a class. And classes then are templates from which objects can be instantiated. This is also very conforming to the norm that you see in Java or languages like that. And there is another concept called subclassing, subtyping, subclassing. And subclassing is the method to derive new classes by adding or overriding implementations. Whilst the type only adds new operations in that in that field, in the definition. Subclassing is then the concept where you actually share behavior and reuse behavior via these structures. Okay, and the last point on our to-do list was open recursion. And for this you have a special variable. Here we call it self. In Java you would have the same concept as this. And this variable allows method invocations on the same object. And in order to do that, self is so-called late bound. Late means the latest point in the execution where you can bind self. And this allows that methods can be invoked in one class and then maybe defined later in some subclass of the first. Whenever you implemented something like a factory method, something that invokes a method that has not been written actually in that abstract class, and then is implemented in the subclass. This is using the late boundness of self. And we call this open recursion because you recurse to the same object, basically, to do that. Now the question, of course, is, this is quite a lot of to-dos, so can we actually do this in the lambda calculus? And the observation that we can draw here from things we already seen is that we also already have some object-like structures in the lambda calculus. We've already seen that. We had like records with fields, records to references, and records to methods, to abstractions, sorry, to functions, containing functions, and this almost felt like object-like. And let's try this. Before we go into something else, let's try that we can use the concepts that we already know to construct something like an object-oriented programming in the lambda calculus. This is now our task. And in order to do that, we need like a notion of what an object actually is. So this is our first point. So the most simplest form that we just learned of an object is a structure encapsulating some internal state and offering some access to the state. So that's the most simplest form of an object that you can ever have. No fancy. So let's define a C, a term C, with this let x equals ref1 in, and now we have a record. That means we have a get, which is dereferencing x, and an increment, which is incrementing x. And that is an object already. So with the let, you create a reference. We discussed this last week, by the way, that you actually need the let here in order to construct that reference and refer to it later. And the type of that object, as you can see, is the definitions basically of the methods, the type definitions of the methods. So get unit to nut, increment unit to unit. And this is rather important because now we have this change between types and classes, because in the type you only get the signatures of the methods, which are implemented just by using records, and the fields of the records are again lambda abstractions. Which means you can define a counter type, which is basically the type of C. It's just a syntactic rewrite here at that point. And now you have like a very simple object. So it has an external state. So no one from the outside can actually, like if you have just C, you wouldn't know how to get X, rather than getting the value of X. So you don't have access to the reference itself, but to the value. Using the C get operation. And using projection, as you can recall, you have this little dot operator using projection. So it's actually C dot get. So again, syntactically very close to home. So let's use this object. C dot inc unit increments X, the internal state, by 1. And then you can write c.get unit. This is syntactically a little bit inconvenient, but you get used to it. Then you get 2 as a natural number. And what you can do is you can, of course, sequence that and then again call c_inc unit, and then c_get unit, and then you get a 4 because you increment it by 2, and then you have that. So this almost feels like object orientation, isn't it? So you have like simple objects that capture internal state. Pretty neat. But you have to do this basically yourself all of the time. And for this, we need object generators. And object generators create and return a new object every time they are called. And this is basically how it works. You take that object definition that you just had and put it into a Lambda abstraction that takes unit as an input. And then you have an object generator. So this thing basically puts out a new object every time you call it. So new counter gets you a new object. Oops, interesting. That's it. I thought there would be another thing. So let me just explain. This is something that you would find very naturally as a constructor. In Java, you don't have to be this explicit about how to construct this. An empty method will suffice, because Java does all the rest in the back. But in the Lambda calculus, you need to do it this way. Oh, sorry. Wow, early. Just human. Subtyping. So now we've seen like object types, simple records of functions, and we can use subtyping of records as the subtyping for objects, for object types. So let's define a new counter type called reset counter that has the get and the inc, but also now has a function called reset in the record. Yeah. And you can define a constructor or like an object generator the same way as this. So you have a function that takes unit, and then with the let you construct a new reference, and you have the get and the inc implementation that you just had. You copy this at this point. We're not doing subclassing, we're doing subtyping. Remember that. And then you have this reset operation, which just basically sets x to 1. And then you can call new reset counter and get a reset counter. And using srcd with, so we didn't introduce any new typing rules. Yeah, remember that. We're just using everything that we've got right now. You already know that reset counter is a subtype of counter, because it has one, like counter has one field less, but get and inc are found in both. So you have a subtyping relationship already. Yeah, with the srcd perm and so on, and depth, you can actually go into the depth and like reorder stuff and so on. But in general, you can just use the subtyping rules for records that we just learned. And I found this pretty elegant, by the way. And now, of course, we now had this like single reference variable. This x is a little bit lame. So let's lift that now from single reference to record of references. So you now have a record, and every field that you use inside of your implementation, you just define as a reference. In this case, we just lifted it one way up. We just put x in a record and redefined this and said, now let R be this record, and then we access x every time through this record R. And now we can have multiple things. So we don't need like very complex let structures with let this in. We can just use one let and have a state all in one place and use a record for that. So you now have a record of methods and a record for the internal state. Pretty neat. And we call this new type for this R a so-called representation type, because this is the internal representation, and this is now the counter representation. And the counter representation is just, as you can see, a reference to a natural number. Pretty neat. Clean that up. Yeah, representation type. Already said that. Good. Now we've done subtyping, and we now want to have inheritance. And as you can see, like these object constructors that we had, like new counter and new reset counter, are basically identical, with this exception of the reset function. And now we want to have things like inheritance, so we are entering class world. So we do want to have primitive classes right now. And how do we do that? We introduce a new term, counter class in this case, which takes a counter representation R. So it's a lambda R counter rep, and constructs an object out of that. So it's a function that takes a representation type and returns an object matching that representation type and the class you've given it. And now, instead of just defining the implementation in the object generator itself, we adjust new counter to just have this representation type and all of its initial values, and then call counter class with R. So we just deferred that, if you can see that. We wrap that into a function and deferred that a little bit. How does this help us? Well, we can now reuse this and say, okay, let's define a new class called reset counter class. And for this, we can use super, because it's the super class. And the first thing that we do is we construct this super class and with counter class and the same counter representation that we just used before. And instead of implementing the get and the inc method ourselves here, we just refer to get and inc. And as you can see, this is not a call. This is actually a reuse of that record field of that super class. So what is super get? Super get, if we just is the result, like a projection on the result of counter class R. And if we just scroll back, counter class R is a counter, and a counter has a get and an inc as a record. So one thing to use this is, of course, like invoking it by putting an argument there, but you can just reuse the function definition at this point. It's a term. We're in the lambda calculus, so it's just a term that you can just reuse at that point. Good. And as you can see, reset we implement ourselves. So reset takes no argument and resets the counter. And as everybody uses the same R here, that's the R that we put in counter rep, that we provide to counter class, and that we use down there at reset. It's the same reference. We can just use the same thing. And then you get a function, this reset counter class class method, a class function, is then taking a counter representation and providing you a reset counter. Pretty neat. And then the constructor for this would be the same thing, but instead of calling counter class, you call reset counter class. And then you get a reset counter. Okay, so now we did inheritance. Pretty good. So this is the thing I explained before. So instead of creating the object directly, we create an object of the super type with the representation we received. Okay, now we've learned how to add methods, but in subtypes, so in subclasses, how do we add instance variables? We might want to have more state in a subclass than in its superclass. So in the counter and the reset counter, we just reuse the same internal representation. But we may want to extend this. And so we may want to have new instance variables. So let's look at this particular example. So you have the get and inc and reset method again, but you have a backup. A new backup method. We already know how to do this. With subclassing, this just works. Okay. But now we also change the counter representation class by adding a new field B for this backup counter rep. Again, remember the equals here is just a syntactic construct. It's just something that we do not to write the same thing over and over again here. But it's the same. You can just exchange it with no step. Good. How does this then work? Well, you write another class function that takes now a backup counter rep and then constructs reset counter class with that backup counter rep. And this is an interesting thing. As we use records all of the time, at this point, when invoking reset counter class, we also look at the subtyping rules for records again. And again, as we added new fields, this doesn't hurt us. We can use the srcd with rule to just reduce it to the other type, and we're good. And this means now that in the backup counter class, we can use this B pretty freely and reset it to the backup variable instead of just setting it to 1 again. Yeah, this is using subtyping. So backup counter rep is quite naturally a subtype of counter rep because it just adds one field, one label. That's fine. And instead of in the reset counter class, we implemented reset ourselves. So we could use super.reset, but we don't want that. We want to set it back to the backup variable. So we can override it. So this is actually how you do overriding in object-oriented lambda calculus, but just setting it newly. This is fine. You can always do this. But how do we call superclass methods? So we just learned 2 different ways to use super in our class definitions. So let's look at this example for a second. So this is a little bit of a funny backup counter. It's not really working quite well, but we can do this. And as you can see, it feels quite natural. So the get is again just inherited from before, but the increment is a little bit different. So this is a function that takes unit as an argument. This is so far the same, but then has a sequence and called super.backup. So what is super? Super is a backup counter class, so we call backup on the super class, and then call super inc at the in the super class as well. So we back up an increment. So every time we increment, we also back up before. So this is basically, so the backup basically becomes a decrement. But then you look how we used super and reset and backup. We just referred to the function again. So 2 different things. In inc, we actually invoke these. These are getting actually evaluated. And in reset and backup and get, we just referred to the original implementation. And as we're working on the same, all the time on the same reference, this just works pretty good. So here is a reuse of the get method, and here is an actual invocation. And this is a particular difference, especially when it comes to evaluating this. Okay, last thing on our to-do list, classes with self. And finally, we want to allow methods of the same object to refer to each other via self. As I cannot do this with the existing example, let's construct a new one. And again, use something like a counter because it's quite interesting, but add a set method. So you have a get and a set method and an increment method. And now we want to implement increment just by calling get and set. You have seen we couldn't call ourselves yet, but let's now do this as a task and implement increment just as a call to gets and sets. So applying the idea of recursive records, and for this we need our fix operation that we learned to love in the previous lectures. And in order to do this, we actually need this fix operation to work a little bit like this. So let's have a look at this. Again, this is a class constructor, not a class constructor. This is a class definition. So we take a counter wrap, but now we wrapped all of the things in the body now into this fix operator, which takes a self, which takes kind of a self reference, has a get and set operation as you would just naturally implement it. And as you can see, set actually takes an argument now, does not return something, it takes an argument called I and sets r.x to that. And increment is self.set of the successor of self.get unit. So now we used self inside of our definition here. This is interesting because it actually has the same type as before. It's again a function going from counter wrap to set counter. But the interesting thing is now self, the fix function fixes our self calling here automatically, unrolling the recursion. Yeah, the fix operation helps us to execute recursions until all operations are unfolded. And again, if you want to understand this more, you can do this as an exercise and just call inc on an object provided by an object generator that uses set counter class. And then just call it and use the definition of fix that we had before, and then you would see that it automatically unrolls all of the self references and will get you to the final result. It just takes a bit. On that note, using fix at this point is not the most efficient way to achieve this, and it actually lacks a feature that we would have. So this might not be the ideal candidate to implement this in this way. And most object-oriented languages support a more general form of recursive call between methods known as open recursion or late binding or late binding of self. And how we can do this is we will remove fix from the class definition and placing it instead at the object creation. And the problem with that is when you do it in the way that we've seen it just before, you have it in the class definition and we'll just unroll it once. The problem with that is that you do not have it on an object basis, and that's why we need to move it down. And this is how it would look differently. So we have this argument self added to setCounter class. We just removed the fix operator and just pull the fix operator in front of the setCounter class call in new setCounter, in the object generator. And in doing so, this actually provides us this open recursion through self. Again, this is something that becomes a little bit more clearer once you either implement it or you do some evaluation on a sheet of paper with just this. So have the two things like compared to each other and try to do evaluations and see how the evaluations differ. And you will actually see that it differs a little bit. And this little bit is actually helping us a lot. However, what I haven't mentioned before is that the type of setCounter class has now changed. So the type of setCounter class is now taking a counter representation and giving you a function from setCounter to setCounter. Because we need to be able to apply the fix operator. And then again, the type of the object generator is not changed. It's again going from unit to setCounter. So this pretty much works the same as before. Interestingly, now that we have open recursion, we can now call methods of a superclass. This now allows us, like when we have methods in a superclass, to allow to call methods of a subclass, even though the subclass did not exist when it is being defined. So the first implementation where we had it in the class definition was more self is now the methods of this class to methods so this is a different thing. Which means that it may be a subclass of the current one. And that's new. And this is actually feeling very natural when we come from things like Java, where this is actually working. We had this in the beginning when we talked about it. Good. How does this look in a complete example? This looks a little bit like this. So let's walk through this one by one. Just a second. Okay. Let's walk through this one by one. So you have this type of the object, which is defining all its methods. It's a get, a set method, an increment, and an accesses method. So the get, set, and inc you can naturally think, but accesses is a number of how many times you've accessed that thing. And that's why it's called instrumented counter. The representation of this has a field x and a label called a, probably for the accesses, but we'll see that in a second. And then you have the class definition, which is, of course, first taking a representation type. This is fine. This is your internal representation. You need that. Then you have the self-reference, with is again the instruction counter, instrumented counter type. And then you construct super by calling the constructor for setCounter class with r and self. And then you reuse the get method and also reuse the inc method, but you do provide a new set method that takes an argument I as a natural number. takes A, this is the number of accesses, and increments that by 1. And then again calls supers.set and provides I. So you basically do the same thing as superset, but before you do increment this A reference. Superinc you reuse again, and then accesses just gives you a dereference to that number. And this is of course of the type instrumented counter representation to instrumented counter as we've seen before. And although when you've seen like in the on the slides before, the inc implementation of the increment implementation of set counter class calls set. Now this is the one we implemented using get and set. It will actually call the one defined here, and this is the neat difference between where you apply the fix operator. This is why we pushed it down to the object creator, in order to be able to do this. And then we explicitly call superset to avoid that behavior, not to get into a loop. So, did we cover everything? Well, all objects that we've seen here belong to the type counter, so we do have multiple representations for the same thing. Fine. Instance variables are hidden by construction. We also did that. That's pretty good. Subtyping. Well, subtyping is ordinary subtyping between records. We made our lives there very easy, so this is fine. And inheritance, this was something that we looked a little bit closer, and there we had a subclass instantiates the superclass working on the same references. And that worked pretty neat. So we're also good here. And then the part where I spent the most time now is open recursion. And we do open recursion through fix, but not at the class level, but at the object generator level to be able to have actual open recursion. So we're good. So now in roughly 50 minutes, we constructed object orientation in the lambda calculus with just the things that we know. We didn't introduce anything new here, no new typing rules, no new syntactic things, no new other things. We just had everything we needed to construct object orientation ourselves. And now we have a fully compatible object-oriented language called the simply typed lambda calculus with the reference extensions that we just had. Pretty neat. Yeah, that's basically it for the first part. I do have a second part on a different system that I will introduce just to you in a second. Before we go into the other topic, are there more questions on object orientation for the lambda calculus? No questions. Okay. Well, I hope you enjoyed the first hour, because I found this to be quite remarkable. I mean, we did have some very low level constructs that we learned, that we just like build up ourselves, and then at some point we just by accident have constructed object orientation in simply an hour without introducing anything new. So with the implementation that you have right now, you actually implemented an object-oriented language. This is quite powerful to be true. So you just implemented a whole new language in the lab yourself that is actually to be like quite equivalent to Java. A little bit less comfortable and a lot less efficient, I would say. But you just did that in like half the course. So if you achieved that, pat yourself on the back. This is pretty neat. Good. Onward to the second part of the lecture. A system called Featherweight Java. So Java itself has the problem that it's not fully formally defined. So we do not have things like full operational semantics and full typing rules for the complete language of Java. As it was a practical implementation, people did not care so much how to formally define this, but more that it just like works on practical programs. And as you've seen, like some of the properties actually are pretty inelegant because of that. Of course, at some point theory and practice should meet. And one thing where they do is an effort called Featherweight Java. So the idea was to take a subset of Java that we can formally specify, and then put it into good use, for finding out theoretical properties about Java and Java-like languages. And that's Featherweight Java. So we're now leaving the lambda calculus for a while and working ourselves into a completely different language model with a different a set of evaluation rules and type system rules. And even though we've just seen that we can model object orientation in the lambda calculus, like the definitions are pretty lengthy, like the syntactic wise it's not very neat. It's a little bit hard to write. You've seen like the full slides of text that I had to do. So that's not very elegant. And we now like leaving the lambda calculus to kind of venture out and to see, can we apply the things that we learn and can we adapt things that we learned to something that is a little bit more based on Java. A word about formal models. So we already saw that like formal models can offer a significant boost to the design of a programming language. And whenever we see like formalization efforts, which are really hard to do usually, and doing the proofs is not something that you do on a Sunday afternoon with a cup of coffee. That's something where you have to sit down, think hard, and think again and again and again, and actually come up with a grand thing and actually get that checked out by multiple people to be able to show this is a real proof. This is hard science and not something you do over lunch. However, in implementing programming languages, you sometimes do not have the time and sometimes you simply do not care. But later on, sometimes that becomes interesting. Because you can see the significant boost that like a definition of that, like a formal definition of that had, and the amount of confidence it gives you when you actually have proven that you can never get stuck in that language. Pretty neat. So a formal model is used to describe a design precisely. to state and prove its properties, and the idea is to direct attention to issues that might have been overlooked otherwise. And in any formal model, be it for a programming language, for anything else, there's always a tension between completeness and compactness. You want it to be, of course, complete, because you want to represent the full world and the actual complete world. And we've seen that for subtyping and algorithmic subtyping, where we actually had a proof for completeness and so on. Here, from the idea of a formal model, another property comes into place, and that is compactness. In order to have your proofs work really, really well, you want to have a very compact model. You don't want to have many cases to check in a case distinction. You want like 3 or 4 or so. You don't want like 50 or 60 cases to check. Practical applications do have the tendency to generate more cases. So the idea in a formal model is usually that you trade this a little bit off, that you trade completeness off for a bit better compactness of the model. And this has been done with featherweight Java. And the more aspects you have in your model, in your formal model, the more complex it becomes. And it's often very sensible to choose a model that is less complete but more compact. This is just what I told you about. This is because in proofs you don't want to have these many case distinctions, and in general you do want to be able to understand and grasp the model rather than to be fully complete. And the idea is to have like maximum insight for minimum investment. And completeness is usually the enemy of minimum investment. And as you might have guessed, this is the strategy throughout the course. This is not something very new here, but something that I applied to the full course. So the models that we work with are not complete, but very compact and very streamlined to understanding them and to work with them properly, other than representing every little teeny bit of a real programming language. Featherweight Java is more on the more complete side, but still leaves some things out. So let's look at a program in featherweight Java. It looks like Java on the first glimpse, but is a little bit different. So the first thing that you will actually see is this explained? Yeah. Is that you actually have an explicit supercall in the object's constructor. In Java, this is done explicitly. Here we use an explicit call to be able to really, in order to be able to really reason about it. If you do something implicit, it's never a good idea to reason about it, because you have to encode it into the rules rather than like working on a syntactic token. And also the subtyping subclassing relation here is made explicit. So in Java, everything inherits from object anyway. In featherweight Java, you really have to make that distinction very clearly. So you can have class B extends A, of course, but if you do not extend anything else, you at least extend object. You can have things like pairs, of course. You can have like fields and methods, of course. And constructors always take all of the fields. You do not have things like a private or public field, but you do can decide how to do this. There is no rule that you actually have to implement these. Constructors, by the way, are the only places in featherweight Java where super and the equal sign appear. You do not have super calls anywhere else here. And this equals is just the only thing that you have here. Whenever you call such a function here, you always return a new pair. So all other methods are purely functional. So we do not have any side effects in Featherweight Java. Featherweight Java is purely functional, so we do not have references to work with. That's something that we actually may have a good use here. But as you've seen, references and side effects make all typing a little bit more complex. The authors of Featherweight Java have actually left that out. And as you can see, these methods are purely functional, and they return just a new object with the changed with this new change first. It's a new object that you get. So what are terms in Featherweight Java? So this is a term in Featherweight Java with this pair definition that we just had. So new pair and new A and new B and set first of a new B gives you a new pair with this. So you have all the time, you have this new operator. New is not constructing something in a sense that you would construct a reference to something. It's just a syntactic construct, and you just evaluate to new values. So it's pretty hard, I know, when you are used to references now and you are used to general purpose Java. This feels way worse. But believe me, for proving properties, this pretty much works fine. You do have costs like this, so you can do something like a pair cast in this case, and you have projections. This .fst and .second, you can reflect the internal state of an object and get that actually out of the object without defining something like this. This cast, by the way, is necessary because, so you see here's a pair and a pair. The problem with that is that the field access first returns a term of the type object, and this is why you need a cast. I quickly go back to the definition of that. Here we are. As you've seen, first and second here, these fields of pair are of type object. So all the projections give you object as type, and so in order to do this, what we've just seen here, and call FST and then second, so first and second here, this would then not type check because we have a declared type of object. In practice, of course, this would work. So actually the evaluation would not fail, but for typing we actually need that. There's a difference, very fundamental, that I have to mention pretty much early on, between the lambda calculus that we've just learned and Featherweight Java. And the lambda calculus uses so-called structural types. That means that names that we use are simple abbreviations. So whenever we had in this previous part of the lecture, things like this set counter and so on, or set counter rep type and so on, these were just syntactic abbreviations. So anything that matches the same structure is the same type for the lambda calculus. For Featherweight Java and other languages like Java itself or Scala and so on, we use nominal types. That means that the type is defined once, and then you can then only its name is used to refer to it. In the lambda calculus, you actually define the type every time you use it, but we, for benefits for reading better, have not done this. So this is the difference between structural and nominal types. So be aware when you read things in Featherweight Java, this behaves totally differently than in the lambda calculus. Nominal type systems have some advantages over structural type systems. And the interesting thing is, like in the nominal type systems, this is much easier. So you have like something like type tags. You can use these as runtime for various purposes, for type testing and so on. This really neat, because it makes implementing things much easier, and you can have like much faster runtime type checks. You can do type testing, you can do printouts of that type, you can do marshalling data structures into binary form, you can do reflection in Java. This is all supported by nominal type systems because you can use these type tags. In a structural type system, you cannot do that because, like, in any use of that type is basically a new type that you just have to match against the existing knowledge of other types that you have, and then define equality all of the time. This is much harder when it comes to testing, printing, marshalling, and so on. Yeah. The interesting thing also is, in a nominal type system, you can do recursive types. You can reuse the name of the type in the same type definition. That's something we couldn't do in the lambda calculus because it was structural and the names would just be like non-existent, yeah, in the actual language. So here you can do actually recursive types, pairs that contains pairs again. Yeah? We can do that. Also, the interesting thing in a nominal type system is that subtype checking becomes very trivial, especially here in featherweight Java, as it's explicitly annotated in the program. So your subtyping relations are actually parts of that. If you have heard the Deka lecture, and if you happen to have made lab number 2, which was the call graph lab in Deka, you would actually know that because there you had to construct your own type hierarchy, which is basically just going over all the classes and capturing all subtype relationships that you have there explicitly annotated, and invert it, and then you basically have your type tree. In structural types typing, you cannot do that. You have to decide that. You have to decide that on the spot every time. It also prevents so-called spurious subsumptions. And spurious subsumptions is pretty interesting because in a structural type system, types might be matched being in the subtype relation, regardless of whether that was intended or not. Yeah. So you did not explicitly in a record type state that one record is the subtype of each other. That is decided by the type checker for you. And you might have unintended subtyping relationships that you never anticipated. In nominal type system, you cannot have that because you explicitly annotate that relationship, and what you did not annotate does not exist. Yeah. So whenever things are like structurally compatible, in the lambda calculus, it works, yeah? But that may not be intentional. No? So let's go to the formal side. This is the definition of featherweight Java. And the first syntactic structure that I wanted to point you is the terms, the T definition. So again, you have things like variables in featherweight Java. You have field projections, so term.field is a field projection. You have so-called method projections. This is an invocation. Yeah? So t.m is a method invocation, and then there's a t with a little ceiling on top of it. And this means that it's a vector, so it can be arbitrarily many terms that you have there. And that means that methods can be called with arbitrarily many arguments. So is the constructor, the new C. It's also a term on its own, and it also takes this T with a ceiling, which is again a vector of terms. And then you have casts of terms, that is kind of the C thing down here. The only values in featherweight Java are constructor calls, also new C with a vector of v. So any featherweight Java program will eventually boil down to something like this. And then you have on the left side class definitions. And in the syntax, it's ordered. So what you do have here is that you have this class definition, which basically says, okay, a class extends a class. And then you have a vector of classes and fields. This is the field definition. So you can have arbitrarily many field definitions. Then have one constructor, and then have multiple method definitions, or 0. That also is fine, but you can have multiple. So one constructor, multiple methods. The constructor is also rather interesting. Oops, sorry for that. Yeah. So just as an annotation, this is a shorthand for C1, F1 until Cn, Fn. So this vector, it's not like class, field. No, it's class, field, and so on. So constructors are very interesting because constructors must take exactly as many parameters as there are instance fields. This is not a choice. You have to do this in featherweight Java, and you have to take all the instance fields as arguments in the constructor. Why is that? Because you pass this all of these parameters into the super call, and then initialize all of these fields. This is this is non negotiable for featherweight Java. For methods, it's always the case that they have a return type and they have a list of arguments. Again, C1, X1, Cn, Xn. Just a pair vector in this case, and a method always has the form that it returns a term. It's purely functional, so it's the only thing that you can do. Let's look at, there must be this supercall, non-negotiable. Subtyping relation is quite as you know it. So you have reflexivity and you have transitivity. So whenever you have a D in between C and E, then of course C is a subtype of E. And the other thing is that when you have a class definition, this lays the grounds for subtyping. So whenever you want to introduce subtyping, you have to have a class definition where this subtyping relationship is explicitly given. CT, by the way, is the class table. This is a table of all the classes, and CT at the point C is basically the class definition of this class C in this particular table. You have all these kinds of tables in featherweight Java, which are a little bit coming from the implementation because you also have that there, and it also makes sense on a theoretical level. This is basically a structure where you look up a class. It's nominal typed, so you have to look it up. So the class table basically holds all the definitions, just as to understand this a little bit better. Good. I should really learn my animations. So the class table is mapping classes to their class declaration. Good. The class table. The class table itself is assumed to satisfy some conditions. So first of all, you have a class definition for every class in your table. And object is not in the definition set of the class table. and for every class name C except object appearing anywhere in the class table, we have a definition. This might seem a little bit redundant with rule number 1. However, the interesting thing is here appearing anywhere in the class table, so that helps us that we have every class that is mentioned either as a superclass or as a return type or as a parameter type. We have a class definition, so the class table is complete. We do not have any open class definitions that we don't know about. The other thing is that the class table also satisfies that we have no cycles in the subtype relation induced by this. That means the typing relation is anti-symmetric. So whenever we have A extending B, B cannot extend from A again. It's there are no cycles, and of course this is anti-symmetric but also anti-cyclic. This means that all of our subtyping is basically a tree and not a graph. Really helpful in practice. We do have some new things that we want to have. First thing is called field lookup, and this is an operation that we just use for implementing all kinds of rules, which basically gives us the fields of a class. And for object, that thing is empty. I'm using here the notation from the original paper, by the way, not to confuse you. It might be a little bit different from the ones you've seen before. In order to be inside of that fields thing, so the conclusion here of that second rule says, okay, the fields of C are the fields of D and C, of course. The fields of D are then looked up again, because you do not only inherit the methods but also the fields. So this is basically also a conjunction operation here, this comma. So you have all the fields from D, from class D, which is your superclass, and all the fields from the class definition from the class table. These are your fields. Method type lookup also looks like this. Also becomes very natural. So whenever you have a method definition in your class table that takes a vector of arguments of the type B, so it can be multiple different types, so B vector, and returns a B, then the method type of that method of that class is this B vector to B. And if M is not defined in this method list in C, that means that it is the method types that it is the same method type as defined in D. You can easily do this. So this is where inheritance kicks in, and you inherit all the methods from D, as long as you extend it, of course. Same for method body. We have an operation that looks up the method body, and this just in a way extracts the term T from this method M of class C. Given that you have all these parameters, this X vector, so you can later on do the substitution. So the method body is not the rare body, but a pair of the arguments and the method body. when you worked with suit before, the method body itself is more like this T and not like the calling context, which is X. In Featherweight Java, it's a little bit different here, but we are purely functional, so in this way, this is fine. And if it's not defined in C, of course, we just take the method body from D, and in object, we do not have anything. Valid method overriding, we need an operator to check that. And in order for something to be overridable, so we have a method M in D that is overridden, where the C vector with this new type, C vector goes to C0. Then we have this. This implies that we have a method type of M in D, which goes from this D vector to D0, and it implies that C is equal, the C vector is equal to this D vector, and C0 is actually D0. And only then we can do valid method overriding. Evaluation rules we can define as such. So we have this projection on new things, which basically gives us the value at that point, which is pretty neat. We do not have any references here, so we can actually evaluate that. So fields are basically, in a way, constants, so we can syntactically take the thing that was given by the constructor. The next rule, this E invocation new, is basically how invocation works. And this should be very familiar to you because you've seen it in the Lambda calculus already. This is the substitution syntax that we had. And so when you do a method invocation, you look up the method body in the premise. And then what you do is you exchange any occurrence of this X vector by this U vector. This is the binding of the formal to the concrete parameter. And then you also exchange this with this new C and the V vector. So this is how they implemented open recursion at this point, is just by substitution and syntactic rewriting. It's a little bit less powerful than the version we've just learned before in the Lambda calculus, but for Featherweight Java, this works in this way quite neatly. The next thing is the cast operation, which basically gives us the inner operation. But as you can see here, we have a runtime type check here. C needs to be a subtype of D, otherwise this wouldn't work. E field is basically telling us, okay, evaluate to a value down, otherwise you don't, you can't project, like the other rules as well. These are just progression rules that evaluate things down to values. And as you've seen, the only values in Featherweight Java are again these new constructs. So this is why all the first three rules were grounded in this new C with the V vector. Good. Again, the other rules, the E field, E invoke recursive, invoke rec value, rec v and invoke argument, and E new arg and E cast are just simple progression rules that help us progress parts of the terms down. And interestingly, this is standard call by value operational semantics. This is not something fancy. This is pretty standard. So this should match up with your expectation of call by value operational semantics. Yep, here the binding of this occurs. We already had that, and this is a runtime subtype check. Good. Typing in the Lambda calculus, and as you can see, it's quite compact. It's 7 rules. It's not very much. The T-var rule should feel very familiar. The T field rule basically tells us that we have to look up the fields of this class C0, which is the class of T0, and then we look up the field at that particular point, and then we get the CI in this case. Invocation is pretty interesting because of one thing. Is this T vector is a C vector. And then whenever we check that, we check that it is a subtype of this D vector. And this D vector is the thing we have looked up in the method type as the input parameter types. This allows us to give arguments that are of a subclass to a method that expects the supertype. Pretty neat. And this is kind of the thing where it happens. This little subtype relationship that thing enables us, and the use of C and D. Same as for new, by the way. There you also have the subtyping relationship, and the fields of C are of type D. So you can also pass other things in there as well. This is what happened with this pair thing in our example a few slides back. There we passed a new pair, and then it got stored. It got stored in this object field, and then when we access it, of course, we need to have the declared type and not the runtime type, which was object again, and then we had to cast. Coming to cast, we have these three rules for casting. So we can cast anything that is a supertype to we can cast anything that is of a subtype to its supertype. Of course, this is the upcast. This also works pretty well. We can downcast if they are compatible and they're not the same. And then we have a senseless cast. That this is a senseless cast. So we can cast basically anything, but we might get warned. So a senseless cast might occur, and we have to allow them actually for proving purposes in featherweight Java. And that's why they're in there. Method and class typing, they look a little bit intimidating, these two rules. They are not. What you basically have here is syntactic constructs that mark you things as okay. These are just syntactic constructs at this point. And what it basically gives us is that the class definitions, method and class definitions, must be conforming to the typing rules as well. So whenever we have let's do the one in the bottom first. So this is a complete class definition, and it says class C extends D with this field vector, the constructor, and the method vector, and this is okay if the field definitions of D, if D has the following field definitions, and the constructor has the field definitions for that supertype and itself. So DG and CF, this is the K definition in the premise. And this, again, is the implementation of that is then super all the G types, and then an initialization of all the fields in this F vector. And then there is a fourth premise which says, okay, the method vector is also okay in C. And to be able to do this, this is the rule above. This is method typing. And this defines a method as being typed okay in C. If we have either an overriding or we have a new definition. And the classes in the class table as such related, and under the assumption that x is typed as C vector and this is typed as C, T0 must be of type E0, and E0 is a subtype of C0. This allows us to return not only the explicit allowed type in the method, but all of its subtypes as well. We may do this. We may return like a specialized pair when we actually were talking about a pair. We may do that. Good. Preservation. The preservation for featherweight Java looks a little bit like this. By the way, how many slides do I have left? Just not to confuse you. Oh, that's not much. Good, we can do this. So this is the preservation property for featherweight Java. It looks almost the same as for the lambda calculus, and this is no surprise. So if we can type a term as a particular class under the assumption of gamma, and there is in this term can take a step, then under the assumptions of gamma, T prime also can be typed as C prime for some C prime sub type of C. So we have preservation, but we may not get the same type, but a more precise one. This is pretty much in line with the preservation property that we have defined for subtyping in the lambda calculus as well. Remember, algorithmic subtyping, that is, we have a more may have a more precise type, but at least the type that we had before. For progress, we actually need a lemma, and this is in a way again the inversion of the rules that we had before. So if T is in this field projection form, then we assume that we have these fields, and if T is in this method invocation form, then we assume that we have this method body. It's not saying much more than this, to be honest. For the actual progress proof, we need so-called evaluation contexts. And evaluation contexts have this notion of so-called holes in them. So each evaluation context is a term with a hole somewhere inside it. And these holes can be later on filled in the proof or in the evaluation. And we write E of T for the whole ordinary term obtained by replacing the hole in E with T. We need this for the proof to work, basically. And otherwise, we have evaluation context for fields, methods, method invocations on values. We have constructor calls and casts, so the forms that we had before. And the idea of these evaluation contexts is they capture the notion of the next subterm to be reduced. We need that syntactically here because the lambda calculus had a very structural syntax and featherweight Java does not. And in order for the proof to work with subterms, we need this notion of subterms in a little bit. And we need like this notion of the next subterm to be reduced because the notion is not much more clearer than in lambda calculus, where it was really like straightforward and given. And this is the property now that we can produce for progress. So suppose T is a closed and well-typed normal form. So this is the thing that you can assume. Then either T is a value, sounds pretty natural. And now comes the interesting case. Or two, for some evaluation context E, we can express T as this form that we have this evaluation context E, and we replace the whole by a cast into C from a new D into a new D of V, where D is not a subtype of C.
And this actually helps us proving progress in this case by straightforward induction on typing derivations. I am sparing you this proof because it's quite lengthy and the educational value is a little bit low, but I do want to have you see the trick that they did with these evaluation contexts. That they can define progress in a way that helps them doing the proof. But just because they had trouble, like the original authors had trouble producing that progress proof with a more straightforward definition, because the syntax of featherweight Java was not helping that in any way to do that proof. And with this evaluation context, they found a neat trick to actually make it the proof tractable, but also work in that syntax. Good. That is based on chapters 18 and 19. 18 the object orientation in the lambda calculus, and 19 the featherweight Java one in the Benjamin Pierce book. Good. We do have some time for questions still, even though the last part was a bit quick. Any more questions from the remaining viewers? Yeah, please do a forum post, because I was also missing parts of your question, and maybe I've misunderstood your question. So please, if you could write that into the forum, the question you asked earlier in the chat, that would be neat. I will just quickly put my answer below that if my assumptions about what you meant were true. Otherwise, I will construct a new answer that answers this. But just so we don't misunderstand each other. Good. More questions on the contents for today? Good. If that's not the case, we stop almost on time. Wish you a very productive week, and we see each other next Wednesday. Thank you very much.